In the last lecture, we studied how the energy bands are formed. Uppermost energy band is called conduction band, and valence band is the band which consists valence electrons. And there is a energy gap in between these two bands. This is the energy gap, and this energy gap is called the band gap. There is a band gap which is denoted by the letter Eg. Now we have to define what is the band gap. You can see that band gap is difference in energy between top of the valence band. This is the top of valence band, and this is the bottom of conduction band. This energy is equals to energy gap. So band gap is energy difference between top of valence band and bottom of conduction band. In insulators and semiconductors. So electron can occupy energies within these two bands, and the gap between these two bands is forbidden region. Okay, let me write. Electron can occupy energies in conduction band and valence band. Within conduction band or within the valence band, and the gap between them, gap between conduction band and valence band is forbidden region. Forbidden region means no energy states are allowed in it. Forbidden region means no energy states are allowed. No energy states are allowed between valence band and conduction band, and we call it band gap. Technically, you can say that band gap is the energy required for electron to move from valence band to conduction band. Technically, we can say that band gap is energy required for electron in valence band to move into conduction band. So you need the energy equals to band gap for electron to jump from valence band to conduction band, induction band. And the band gap is constant. Band gap is constant for the material. but it slightly varies with temperature. For example, silicon has band gap 1.1 electron volt, which is constant. Slightly it may change with the temperature. And germanium has band gap around zero point 0.7 electron volt. This also changes with the temperature. And hence, in the semiconductor, like silicon and germanium, current increases with the increase in temperature. That is because electrons get more and more energy, more and more electrons are excited into conduction bands. So this was about the band gap. We are going to classify the solid based on this band gap. Okay, classification of solid. So materials are classified into conductor, insulator, and semiconductor by energy gap, or you can say based on energy gap between conduction band and valence band. So let's see one by one. First, consider conductor. Conductor, the first material we are considering, the conductors. In conductor, it is observed that valence band is half filled. Valence band is half filled. Or if it is completely filled, if valence band is completely filled, then it overlaps with conduction band. So these two situations can be observed in case of the conductor. So let me show the diagram for the half-filled valence band. This is the valence band, and this valence band is half-filled. Energy levels below this are occupied by electrons. All these are the energy levels, and they are occupied by electrons. And all the energy levels above this are empty. And electrons in lower energy levels have access to upper vacant energy levels, as very large number of vacant levels exist, and then the large current can flow in it. Because as I said, that this is actually a band. In this band, if this is a S band, then there are n number of energy levels which are very closely spaced. So they looks like a band and not individual energy levels. If it is a P band, if the P band is half filled, then it will have 3n energy levels. And these 3n energy levels also are very closely spaced. So what happens? The electrons which are in the lower energy levels, are having enough number of empty energy levels to move in. There are several energy levels here, so these electrons can move into these energy levels. And those electrons are free electrons for the conduction. An example of this half-filled valence band is trivalent metals. Trivalent metals means they are having three valence electrons. So the trivalent metals form half-filled valence band. And examples are aluminium and gallium. So this is in case of half-filled valence band. Next possibility is if valence band is completely filled, then it overlaps with the conduction band. Let me show that. This is the valence band, and this valence band overlap with conduction band. This is valence band, this is conduction band. In this case also, valence band is completely filled, but it is overlapping with the conduction band. So electrons here, have can easily go on this on the in this energy levels because there is very small energy difference between them, and electron can easily go there and occupy that energy levels. That electrons are free for the conductions. And example for this is divalent metals. For divalent metals, there is overlapped conduction and valence band. And examples for this is magnesium, calcium, zinc, cadmium, etc. These are the examples. So in conductor, there is no band gap available, and lot many energy levels are free for electrons to occupy, and those electrons are free for the conduction. They are not bound in the structure. Then second one is consider the example of insulator here. Insulators. This is the conduction band in the insulator, and here is valence band. And this is the energy gap between them, Eg. So most of the substances are insulator. In this case, in case of the insulator, uppermost band, which we are calling valence band, is completely filled. So this valence band is completely filled. And there is a large energy gap between the valence and conduction band. There is a large band gap between valence band and conduction band. Generally, it is more than the band gap Eg is more than 2 electron volt. So, since the band gap is very large, it is difficult for electron in valence band to absorb such a large amount of energy from the ordinary applied electric field in order to jump into conduction band. Okay, it is then since the band gap is very large, then it is difficult for electron in valence band to absorb such large energy from ordinary electric field strength to jump from valence band to conduction band. So it's not possible for electron to absorb such a large energy. Electric field applied is ordinary electric field applied. So electrons cannot gain enough energy to jump from valence band to conduction band. So conduction band in this case is almost empty. Conduction band is almost empty. So conduction band is empty. No electrons are available for conduction. So no current will flow through the insulators. Then the third example is semiconductor. Semiconductor is intermediate. It is intermediate. That is, it is in between insulator and conductor. It has small energy gap. That is, in this case, Eg is less than 2 electron volt. So let me show that diagram here. This is the conduction band and this is the valence band. And this is energy gap Eg, which is less than 2 electron volt. So some electron jump from valence band to conduction band, but it leaves vacancy behind, which we call hole. So let's say at T equals to 0, that is at absolute 0 temperature, at T equals to 0 Kelvin, valence band is completely filled and conduction band is empty. So at T equals to 0 Kelvin, semiconductors are insulators. Behaves as insulators. But as the temperature increases, the electrons in the valence band gain enough energy and they move into conduction band and leaves behind the vacancy. So what we can say is some electrons at room temperature gain enough energy to jump from valence band to conduction band, leaves behind vacancy called holes. So there are holes in the valence band, electrons in the conduction band. And when electric field is applied, upon application of electric field, what will happen? Electrons in conduction band gain energy, gain we can say the kinetic energy and conduct electricity. At the same time, holes in valence band also take kinetic energy and conduct electricity. So there are two types of current. There are two charge carriers in the semiconductor. Electron flows in the conduction band, holes flow in valence band. So two charge carriers available. And example are germanium and silicon. Band gap of germanium is around 0.7 electron volt and that of silicon is 1.1 electron volt.